Alright, so let's see another weak acid, strong base problem. We have some ascorbic acid, and it gives us the mass of the acid. It tells us the volume of the solution. It says we're titrating it with a strong base. It gives us the molarity of the strong base, and it tells us when equivalence point was met. And so we're going to use that to figure all this out. First off, we're going to find the molecular weight or molar mass of the ascorbic acid. It tells us the ascorbic acid can be represented as HA. It's a monoprotic acid, and so that means that these are going to react in a 1-to-1 ratio. So if I have the molarity of the base and the volume of the base, I can find the moles of the base. Then moles of base will equal moles of acid. Then I've got grams of acid, so I can use that to find molar mass. So here's our moles of NaOH. And like we said, since this is a monoprotic acid, that means it's a 1-to-1 ratio with the acid, so it's also moles of the acid. And we have mass of the acid, so we can take grams divided by moles, and we get our molar mass. Now the next part of the question says when 20 milliliters of NaOH, so that means we have not reached equivalence point yet, has been added, the pH is 4.23, and it wants us to calculate the acid equilibrium constant. So it wants us to calculate Ka. Now if we have not reached equivalence point yet, that means this pH is dependent upon the weak acid. So the NaOH is being all used up, and all you're left with is the weak acid, which is where the pH is coming from. We can use the pH to calculate the hydrogen concentration, so I'm going to go ahead and do that. And we can also use our equation for the addition of the hydroxide ion to the acid to figure out how much of all of this we have left over. So I'm going to go ahead and start plugging stuff in. Now we already saw there's 0.0078 moles of HA. Now we're only adding 20 milliliters of the NaOH, so we need to recalculate the moles of NaOH that we're adding to this. So we're adding about 0.0044 moles of the OH. Now if I go ahead and figure this out, we're assuming all the OH is being used up. So all of these are going to be changing by 0.0044. And we can use this to find our equilibrium value. And just like in the last problem, keep in mind these are moles. So before we can plug them into anything, we've got to turn these into molarity, into concentrations. So we had 50 milliliters of the acid solution. We just added 20 milliliters of NaOH, so that means we have 70 milliliters altogether. So I'm going to divide both of these by 70 milliliters, and I'll get the concentrations of the HA and the A negative. And now that I've got this, I can use these values here for HA and A negative and the value for H positive to find the value for Ka of the acid. I can do that like this, where this is my equation, and so my equilibrium expression would look like this. And I can just plug in the numbers that I got for H plus for my conjugate base and for my acid. And then I can take that and solve for Ka. And I get about 7.6 times 10 to the negative fifth. Now this isn't the only way that you can go through and do this. You can actually skip this step up here and just go ahead and do this part right here. Find your values for your acid concentration and base concentration, and then you can use the Anderson-Hasselbalch equation because you have the pH, so pH equals, and then your pKa, you'd be solving for your Ka of your plus the log of your acid over your, or plus the log of your base over your acid. Either one of those you should get about the same answer, so either one is fine. The next part of our question is asking us to calculate the equilibrium constant for the reaction of the ion with water. This is pretty much asking us for the K value for the conjugate base, A negative. In other words, it's just asking us to solve for Kb. And if we have Ka, then we automatically know what Kb is, because we can use that Kw expression to find that. So remember that Kw is 1 times 10 to the negative 14th. That's going to be equal to Ka times Kb. So I plug in my Ka, and I should be able to find my Kb. And I get about 1.3 times 10 to the negative 10th. Now for the last part, we're going to find the pH at the equivalence point. This is a real common question. Since we're at equivalence point, remember that the pH is not going to be 7, because this is a weak acid, strong base reaction. The pH is going to be above 7, and the reason why it's above 7 is because of the conjugate base, the A negative from that weak acid. So this pH is all about the A negative. So when we write the equation for what's actually causing the pH, we're focusing on the A negative and what it does. How does the conjugate base of this weak acid cause a pH change? We're going back to our hydrolysis equation. So first I'm going to start with the hydrolysis equation showing the reaction of A negative with water. Now at equivalence point, that means all of the NaOH and all of the acid have reacted stoichiometrically, and since they were reacting in a 1-to-1 ratio, that means that the moles of these, which was 0.0078 moles if I look back at part A, the moles of the acid and the moles of the base are going to react together, and they're going to make moles of that A negative. And the moles of the A negative are going to be equal to the moles of that acid and base, since it was a 1-to-1 to 1-to-1 ratio. And so that means that I've got 0.0078 moles of A negative that's being made here. But this is moles. I want it in concentration, so I need to divide that by the volume. The volume was 50 milliliters of acid plus 35.23 milliliters of base, because that's what it was at equivalence point if I look back at the problem. So I need to divide this by that total volume. And when I do this, I'm going to get a concentration of about 0.095. Now that I have this concentration, I can go ahead and finish up my ice table. These all start out as zeros. This is going to go down by x, increase by x, increase by x. It's going to be 0.095, x and x. Now, this is my conjugate base, so I can use the Kb that I figured right here, which is the Kb, the conjugate base equilibrium equilibrium constant, and I can plug that into my equilibrium expression. And I can take this and I can go ahead and solve for x, and this x is equal to the hydroxide concentration. So if I plug this into a negative log equation, I'm actually finding the pOH, and then just subtract 14 minus 5.46, and that'll give me the pH. And that is how you deal with these problems. The hard part about this is you're dealing with multiple reactions. You're dealing with an acid reacting with a weak base, but then you're dealing with, the weak acid dealing with strong base, but then you're dealing with the conjugate base of the weak acid reacting with water. There's quite a lot going on here. Really, the only way to get good at these is to practice them. So be sure and practice your homework several times. Go back and watch this example several times if you need to, or try some of the ones that are in your book. Whatever it is you need to do, because you can't get good at these or understand them just by watching this. You have to practice, practice, practice to get good at these problems. Now for weak base strong acid reactions, you just do them the exact same way. Nothing different. The only thing that's different is the pH is always going to be less than 7 at the equivalence point of these types of reactions. And you can probably guess why. It's for the same reason that the other one was greater than 7. It's because the conjugate acid of your weak base is undergoing a hydrolysis reaction, and that causes the pH to lower. If you're comparing a weak acid strong base titration to a strong acid strong base titration, first off, your solution of your weak acid is going to have a higher pH than the strong acid. Strong acid may be around 0, weak acid may be around 3. The pH change is not going to be nearly as much for a weak acid strong base than it would be for a strong acid strong base, which makes sense. If you're going from 0 to 14, that's a much greater change than going from 3 to 14. and your equivalence point is going to be above 7, like we've been saying. Now for a weak base strong acid, the solution of your weak base is going to have a lower initial pH than the strong base. Your pH change is still going to be smaller. Your pH at equivalence point is going to be less than 7. So it's exactly like those titration curves that I showed you at the very beginning of these notes. All right, and then the very, very end of this is polyprotic acids. Y'all have already seen this with your lab. The neutralization happens in 2 steps, and so you end up with 2 equivalence points. And y'all saw how to do this with your lab, how to use that to find your pKa's and your Ka values by using half equivalence points.